Hello, this is part 3 of 4 videos for Chemistry Paper 2. This video is looking at something called chemical analysis, and there's not very many things on this video to learn, but they are all really important. So the first thing we're going to have a look at is something called a formulation. A formulation is a mixture which has carefully been designed to have specific properties. So if I put certain chemicals together, they will do a certain job. So for instance, paint, medicine, fuels, alloys, makeup, chewing gum, anything where chemicals have been put together for a specific job is a formulation. And it's making sure you use that word designed because of their specific properties. Now, looking at the second part of this topic, we are looking at one of the required practicals. And there are 3 required practicals in paper 2. You've got rates of reaction, chromatography and water purification. And this is the second one. And the exam board does like this one because they can start to get their math skills tested in this particular practical. So forensic science uses this quite a lot because they want to work out whether the piece of evidence they've got actually matches to some a suspect's maybe pen, for instance. So if someone's written a particularly incriminating letter and they want to work out who's written the letter, they will get the pens from people that they think would have written it, and then they will actually work out what they look like. So let's just say this is 4 suspects. So A, B, C and D, and they've got 4 pens. And I've just done them in colours just to sort of try and help you to see what's going on. But essentially these would all be one colour. So this is person A's pen, and you can see that the solvent has dragged the constituent parts up to this point. B, this pen has gone up to here. C, this pen has gone up to here. And D, this pen has gone up to here. So I want to know whether X is one of these pens. And actually I could work out that yes, X has got some of B's ink in it, and yes, X has got some of D's ink in it, but it doesn't specifically match a particular pen. So what you can say about this is X contains B and D, it does not contain C and A, and that would be a good answer because I'm talking about all the points. When we're looking at chromatography, first of all, you must always make sure that this is a pencil line at the bottom that you use. And the reason for that is because if I used pen, the ink would dissolve in with the samples that I'm trying to test, and that would give me a false result. So I put my pencil line at the bottom, I put my sample dots on the line, and then I dip the bottom end of this paper into some water. The water then drags up the paper. Now, the water is also known as the solvent. It doesn't always have to be water, but it is usually when we're talking about it in the classroom. That is dragged up through the paper. We call the solvent the mobile phase because it is moving, whereas the paper is the stationary phase because it's just sitting still. Now, during chromatography, mixtures are separated into their constituent components. The solvent dissolves the sample and carries them up the paper depending on its attraction for the paper and for the solvent. Now, we can actually carry out a calculation from chromatography, and it's the RF value, and it's the distance moved by the substance divided by the distance moved by the solvent. So my substance will have gone from there to there. I can work out that distance. So if I go from there to there, that there, and I usually go to the centre of the point, and I usually need to get a ruler, especially onto the exam paper, and I need to actually measure from there to there. And that is the distance moved by my substance. And then I go from the line here all the way up to the line at the top, and that is the distance moved by my solvent. I take those 2 numbers and I put them into this calculation. Distance moved by substance divided by distance moved by solvent, and I get an RF value. And the RF value is always 0 point something. So if you get an answer that's 1 point something or a number that doesn't make any sense, then you've done it the wrong way round. It's substance divided by solvent. Common mistakes. The pure substances produce a single spot in all solvents. Okay, so making sure you get that single spot and where you're measuring the RF value to. Also, as I said before, only ever using pencil to draw the start line as the ink will dissolve and affect the results. So essentially that's the required practical, and I think you could pick up a lot of marks on that one. Gas tests is the next part of this topic. So making sure you understand the properties of the different gases and how we can test for them. So hydrogen is a highly explosive gas, and if we set fire to it, it makes that loud pop sound, that squeaky pop, because when it's reacted with oxygen, as I said, it's really explosive and is really dangerous. So which is why we only make small amounts in the lab. Chlorine is a green gas, but it can bleach dye. So when we're testing for chlorine, we use damp litmus paper and it turns it white. You must make sure you say that it's damp, because that usually is the second mark, because that's usually a 2-mark question. How do I test for oxygen? Well, oxygen is a gas, again, that helps fuels to burn. So if I had a glowing splint, so I'd light the splint and I would just shake it until it went out and it was just glowing around the edge. If I pop that into a jar of oxygen, it will relight the splint. And then lastly, carbon dioxide. Carbon dioxide is a colourless gas, but it's quite heavy as well. Whereas hydrogen is really light and will float away, carbon dioxide is really heavy, and I can then use that to bubble it through lime water, and it makes the lime water go cloudy. So, hydrogen gas, squeaky pop. Chlorine, damp litmus paper turns white. Oxygen, relight a glowing splint. Carbon dioxide turns lime water cloudy. And the last thing I just need to talk about in this video is whether a substance is pure or impure. Now, every substance that we know that is pure has its own melting point and boiling point. And I always use water as an example because it's really easy to remember. Ice to water, water to steam. The melting point of ice, solid to a liquid is 0 degrees, and liquid to gas is 100 degrees. Now that is specific just to water. So if I carried out this experiment and I found that the ice melted at 2 degrees or it boiled at 105 degrees, that would tell me that that is not pure water. There's something else in there. So you have to have a pure substance. Now, pharmaceutical companies use this a lot to test the purity of their drugs, because they need to make sure that they are not adding different chemicals, because that could cause side effects that they don't want. So aspirin, for instance, is a tablet some people take to that need to treat pain or fever or inflammation. Aspirin has a specific melting point of 135 degrees and a specific boiling point of 140 degrees. So when they test aspirin tablets, if they do not melt or boil at those temperatures, they know that there's other impurities in there which could cause, like I say, could cause side effects. And every chemical that is made has got its own melting point and boiling point. So as I said, this was a short video, part 3 for chemical analysis. This is paper 2 for chemistry. There's one more video for paper 2, and thank you for listening.